Hey everyone. Uh, as I'm doing these videos, I upload them. I haven't emailed out any emails. Somehow I got 8 views on that first video. Who are you? Who's watching this? Other than my students. I hope my students are watching it, but I hope you have stuff to do. Like, I don't know, astronomy homework or something. Anyway, there's plenty of stuff to do, but I haven't taught on any of this stuff, so it's kind of, oh, what do we do? I want to talk about a different type of problem that you might see. Mm, I have to go back and look at the homework and make sure that you're going to see some of these problems somewhere. Certainly, I want you to have experience with them. And I'm going to pose this as a problem where we have two things moving. In this case, we have a speeder. Say I'm driving to work and I'm going 20 meters a second, but the speed limit's 15 meters a second. And, that's not a horrible joke. That could be something like 35 miles an hour. It was ballpark, but we're sticking with metric. And so we have I'm going at constant velocity. And the cop sees me when I'm 60 meters in front of him and stands on the gas. And so he has an acceleration, but he was parked. And so what we want to know is, one, where am I caught? And two is when. So what those ultimately mean is if we draw this out somewhere else, both the car that I'm driving and the cop car should be at the same location and at the same time. T final. So if we organize our information, and I'm going to do it by color, here's the cop's information. We're going to put, as an example, you can put your 0 anywhere. I'm going to put it here. X is 0. So he has X initial is 0. X final is one of the things we want. V initial is 0 because he's at rest. V final, we would like to know that as well. How fast does a cop have to go to catch me? The acceleration we know is 7 meters per second squared. And the time, well, we don't know that. That's part of the questions. And when we look at this, there's really 6 variables, and we only know 3 of them. And, if we do this as delta x is something, then there's 5 variables, and we only know 2. So we don't have enough information here to apply any of the equations that we knew before. Let's see the speeder. Well, they have X initial is 60 meters because we're both sharing the same coordinate system, so we both have the same x equals 0. But X final, we don't know, and delta X, we don't know. V initial is our 20 meters per second, and V final is also 20 meters per second because it's constant velocity. It can't change, and because it can't change, the acceleration is 0. So our acceleration is 0, but our time is, well, I don't know. So we're kind of stuck here, is that most of our normal equations depend on V initial and V final changing. We kind of don't have enough information. Is what determines what X final is the time, but the time is set by what the cop does. So we kind of have to solve both of these at the same time, right? We do have a way of solving this. We can say, well, based on this, V average is 20 meters a second. That's just the average of those two numbers. And that is just delta X over delta T. So we can say delta X for the speeder is 20 meters per second times delta t. Now, whatever happens, the cop has to travel 60 extra meters to meet at the same spot. So we can also say that delta x for the cop is delta x for the speeder plus 60 meters. We have some extra information there. And then we can look at the cop's information, and we realize that we have the initial, we have x initial, we have the acceleration, so we can write an equation that looks like delta x sub c. What's going to be v initial times time plus 1/2 a for the cop times t squared. So every time that I have a distinction between these things, I should put in a little subscript, like the acceleration for the speeder is 0, the acceleration for the cop is 7 meters per second squared. And so when we look at this, we also realize that, well, the initial velocity is 0, so we don't care about that term. That goes to 0. And so what we can do is write an equation based on these three. Right, is that we can take this middle one and we can substitute in the other terms. Right, because essentially what we're doing is saying t equals 0 here, so we can drop this delta t. And we'll have t final over here. And so this will just be the elapsed time, and so will this. So when we have that written out, what we'll get is something that looks like, well, we're going to take this middle equation and we're going to plug in. So we'll have 1/2 the acceleration for the cop times t squared equals, and then we'll have the term for the speeder is 20 meters per second times t plus the 60 meters. This is ultimately the thing that gets us, but we need these other two as well. So once we have an equation like this, we can start trying to solve it. So we rearrange this a bit. This is going to be a thing where we ultimately have a quadratic. We're going to have, we can start plugging our numbers in. 1/2 7 meters per second squared times t squared. And then we're going to have this 20 meters per second times t. And that's going to be subtracted over. So minus 20 meters per second squared times t. And then we have this 60 meters we subtract over. Minus 60 meters is 0. And so we realize if we check, this time will cancel these units, we'll have meters. This time will cancel this, and we'll have meters. Everything's going to be in meters, so we can drop the units. We can simplify this. This is 3.5 t squared minus 20t minus 60 meters, and that equals 0. Now, if you're on a test, quadratic formula, right? We'd go in and we say, hey, this is our A, this is our B, this is our C. And so the solution should look like minus B plus or minus square root B squared minus 4AC over 2A. And so what we should get is that this looks like 20 minus 20, and then the minus sign there cancels, plus or minus square root 400 minus 20 squared is 400. And we have 4 times 3.5 is 14. So I'll just write it out. 4 times 3.5 times 60. And we have a minus 60, so that's going to change that to a plus, so we're good. You do have to check that this thing is positive. And then we'll have 2 times 3.5 is 70. Or sorry, is 7. And so we can check. We can go through and do our calculations. This is going to be 20 over 7 plus or minus. We'll figure out what this thing is over 7. And on our calculator, we do 400 minus 4 times 3.5 times 60 with a negative sign. That is 840 we're subtracting off, and we get 1240. And so we will have solutions that look like, well, if we're going to take the positive sign first, we'll divide this by 7. So this term is 177.1 seconds. This term is 20 divided by 7 is 2.9 seconds. Well, and this is plus or minus. So if we take the positive number, T could be 2.9 plus 177.1 should be 180. Or T is 2.9 minus 177.1 is minus 174.2 seconds. So now we inspect our solutions. We have two solutions. One is obviously right, one is obviously wrong. You can imagine if you're driving along in this problem and a cop tries to pull you over, it might take 3 minutes. This is 20 meters per second times 2.25 is 45 miles an hour. And, it takes time for the cop to accelerate up to speed. So this time, it could be 3 minutes. What the minus sign here is saying is this could be 3 minutes in the past. Before you ever got here, somewhere off to the left of the screen, he pulls you over. And that can make some sense. Well, if we plot this, right, there's our plot, and we're going to extend this axis over, and we'll do x and t. What we're saying is there's a point here at 180 seconds, but there's an almost symmetric point over there, and the plot looks like this, where this delta x is the separation of the cars. How far apart are the cars? Well, when you pass the cop the first time, then the cop starts its motion. You should really be somewhere on this where you're 60 meters away, say here, and then you go up to your maximum value, and then the cop starts gaining on you, and you go to 0. So this time over here is a phony one. It's a mathematical solution, but it doesn't match the physics. You have to consider what's going on in the physics. So that says this is our time 180 seconds. That means we can immediately jump to where did I get caught? Our delta x for the speeder is going to be 20 meters per second times 180 seconds. All right, and that's coming from our equations up here. The V average is delta x over delta t. And so we go with this, and 20 times 180 should be 3,600, is 3.6 kilometers, 3,600 meters. It's a couple miles. That's not a horrible, that might not make a lot of sense because cops probably accelerate a bit faster than this. These are just numbers made up for the problem. We can ask one more question. What is the cop's final speed? And if we do that, well, we can just do V final is V initial plus AT. The cop has to drive for 180 seconds and starts at 0. So it'll be 180 seconds for time times 7 meters per second squared. And 180 times 7 is 1260 meters per second. And so we realize that your instructor probably wrote a silly problem. Now, this is not a believable speed. Kilometers per second is not believable, but, you know, sometimes I do just make a mistake in designing a problem. It's okay. Um, but that is particularly why I asked, your text will ask, hopefully, sensible questions. But you do have to check your work. So I've got a few minutes here. I want to do another type of problem. This is primarily for people doing calculus. All right, is it? We kind of just want to go through and say, if we have a function, can we figure out what's going on with it? Like, let's say I have x of t is 10 minus 8.5t plus 3t squared. All right. And so we can ask, what is the velocity and the acceleration functions? And what we would do is say the velocity is the derivative with respect to time of the position. And we take a derivative of each term. So the derivative here of 10 is 0. The derivative of our velocity bit is, well, derivative of t is 1. So we have minus 8.5, just have the coefficient. And then the derivative here is 6t. Then we can go and say, well, what is the acceleration? Well, that is dt of v of t. When we look at that, well, the derivative of 0 is 0, and the derivative of this constant term is 0. And so the derivative of this is 6. And we put in some units. And then so we can kind of read it off of here. This is 6 meters per second squared. This is 8.5 meters per second. And so these things had some units in here, right? You have 10 meters minus 8.5 meters per second times t plus 3 meters per second t squared. And so if you know the form of your equation, this thing that we're treating like constant acceleration has to look like x plus vt plus 1/2 at squared. You can jump from this and say, well, the velocity has to be 8.5, and the acceleration has to be twice this coefficient. It is. So we're going to keep going here for a minute. I'm going to do another problem. What if you have more terms? Well, actually, let's go and say, what if you have a specific time you care about? So let's do x of t is 12 plus 4t minus t squared. And then we're going to say, well, what is the velocity at 5 seconds? Well, that is the derivative with respect to time of x at, so it's x of t, and then we evaluate it at t is 5 seconds. We take the derivative first, and then we evaluate. And so if we do this, derivative of 12 is 0, the derivative of this term is 4, and the derivative of this term is minus 2t, and we evaluate at 5 seconds. That is 4 minus 10 seconds. And we need to put in some units. This is going to be meters per second and meters per second squared. So meters per second squared. Oops. Let's just start that over. We're going to have 4 meters per second minus 2 meters per second squared times 5 seconds. And that's going to be 4 minus 10 is minus 6 meters per second. If we interpret it, this is, say positive is to the right, This is motion. It goes this way to start with, and then it slows down, it stops, and it turns around. It moves to the right first, and then moves back to the left. And if we want to know the acceleration in this problem at a certain time, well, once we take the derivative of the thing that we worked with, right, our v of t is 4 minus 2t. Well, the derivative of that is 2, or minus 2. So a of t is minus 2, and we just say, well, it's minus 2 meters per second. So, that said, let's do another problem. I've got 5 more minutes that I'd like to spend on this. Let's say that x of t is 6 minus 3t plus 5t squared plus t cubed. What do we do with that? What this t cubed says is we're not using constant acceleration, is that when we calculate the acceleration, it will depend on the time. What we're doing is we're pushing harder as time goes on. We're changing the forces involved on things. So we can just do the derivatives, get to the acceleration. V of t is, we take the derivative of 6 is 0. The derivative of minus 3t is minus 3. The derivative of 5t squared is 10t. And the derivative of 3 cubed is 3t squared. So we'll save some space, because what we're going to eventually do is say, what is v at 5 seconds, and what is a at 5 seconds? And we could say, what is x at 5 seconds? And we'll do that too. So for the acceleration, we're just going to take the derivative of this term. So the derivative of these two terms are 0. And for 10t, we have 10. And for this t squared term, we have 6t. That's it. So now, when we want to calculate our values at a particular time, we evaluate these at those times. So a of 5 seconds is 10 plus 6 times 5, and that is going to be 40. And we should have some units here, right? Is that this thing has a unit of meters, meters per second squared, meters per second cubed. And so as we go down through these, this should have units of meters per second squared, and this is meters per second cubed times seconds, meters per second squared. So we do the same thing with the velocity. What we have is minus 3 plus 10 times 5 seconds plus 3 times 5 seconds squared. So we have minus 3 plus 50 plus 3 times 25 is 75. 125, 122 meters per second. Again, we're doing our units, meters, meters per second squared, meters per second cubed. And so everything will cancel out to meters per second. And so finally, this term has a hidden coefficient of 1. So everything in the top will turn to meters. X of 5 seconds is 6 minus 3 times 5 plus 5 times 5 squared plus 5 cubed. And that is, let's see, that is 6 minus 15 plus 5 times 25 is 125 plus 5 cubed is 125. So we have 250, 235, 241 meters. It's that simple. All we do is, if we need the velocity, we take derivatives. If we need a specific time, we plug in after we get our formulas. You've seen this if you've been through Calc 1. I'm pretty certain you've calculated derivatives at a particular value for your variable x. Now, later on, we probably want to do things like talk about graphs. If you have a graph and it has some value, let's say it looks like that. So this is x and t. If we want to know, if we want to inspect this and read off, the values at particular points, and we want to know what the velocity is here, and maybe here, and maybe here, and here, what we have to do is figure out what is the tangent line to those points. And for stuff that's linear like this, it's going to be rise over run. There's some value that you can read, and some other value you can read, and you can do rise over run for these. And in here, you can see the value stays the same. If delta x is 0, then v is 0. All right, so you can figure out the slope, the tangent lines, by doing this. And the idea is that you don't have to do it right at that point if everything's nice and linear like this and you're just asked to interpret a graph. You just go and deduce the slope from rise over run. All right. So that was 3 complete asides. That's going to end things. This is 27 minutes in, so very, very carefully, I want to show y'all. So, of course, I work at home. That is my beautiful baby cat, Frances. I love her so much, and that's sufficient. This is my little bit of workspace that I have. If I show you over here, I have electronics that I'm working on when I'm not doing school, which, basically that's over and I need to clean up. And I have paper and a cat. And that's all you really need to do physics. And maybe a calculator, but people have done physics without it before. It just takes longer. So I hope y'all are enjoying these, or at least I hope that they're useful. And I do want to hear feedback if there's anything else you need. There's going to be more videos, but probably tonight I'll just record something for astronomy so that they get something, because I've done too many physics videos as it is, and I'll call it a night. If you're watching these before Thursday, then we'll have a jigsaw session on Thursday. If you're watching these before Friday, we'll have mentor meetings on Friday. And mine are at 3 p.m. Miss Arnold will be there, and you want to get to know her as well. And she'll help me be, less like a physicist and more like a normal person. And Saturday is the Saturday study sessions that we would have in person. They're going to be on Jigsaw, 9 to 1. You've gotten links to all these in email, so please consider coming for a few minutes. You can get to know us. You can ask questions. There's certainly enough work out there for you to do it. All right, that's 30 minutes of video. Y'all have a nice evening.